ones are strict, actual physical interactions. And the hydrophobic effect is really kind of an illusion, right? So let's say that you're making pasta, right? And you sprinkle some olive oil in the water, right? Which you're not supposed to do. But you sprinkle some olive oil in the water. And what ends up happening, right? Well, all those oil droplets, if you leave them alone long enough, they'll form one giant droplet in the middle, right? Now, how can that be the case? Because if we think about oil, right? Well, it's uncharged, it's non-polar. So there's no ionic interaction between them. There's no hydrogen bond interaction between them. They're too far away for van der Waals interactions to actually matter, right? Because we're talking about centimeters worth of distance, whereas van der Waals interactions are talking about angstroms, right? So those don't even come into play. So how do they coalesce together to form that big oil droplet? Well, the answer is that they don't, right? It's just the lowest energy state of the system in why. Well, it actually has nothing to do really with the oil droplets, or in this case, these non-polar molecules like you see in the bottom. Because when we have a non-polar molecule, or that oil droplet in the pan, or in the water, right? Well, they can't form any hydrogen bonds with the water. And what does water love to do? It loves to form hydrogen bonds. That oxygen can be that H bond acceptor for two different donors, and each water molecule also has two hydrogen bond donors. So each water molecule is able to form a maximum of 4 hydrogen bonds with neighboring water molecules. In fact, the number of hydrogen bonds that are formed, right, is simply a function of what phase the water is in, right? 4 hydrogen bonds, right? What is that? What do we call water when it's forming 4 hydrogen bonds? Take a guess. No. Take a guess. Is that a trick question? You probably had some today. Starts with ice. It's ice. If we have 3 or 2 hydrogen bonds, what do we call that? Yes, it's just water. And if we have 1 or fewer, you can't, well, yes. Steam. It's steam. You know words, right? So, what happens now when we drop this nonpolar molecule or this oil droplet into the thing of water? Well, it can't form these hydrogen bonds anymore, so these water molecules are very unhappy and end up forming this kind of cage, right? This cage around this nonpolar molecule. These are ordered, right? They can't form as many hydrogen bonds, so this is not the lowest energy state the system can be in. Instead, if we were to put these two together, right, these two together, we're smushing together, well now, all of these water molecules down here, and all of these water molecules over here, are now free to go hang out with their water molecule buddies, because this face here is now no longer covered by that cage, right? So we've reduced the surface area, and now we've increased the amount of water that's out free, able to make hydrogen bonds. So now we're at the lowest energy state of this system. So how did these two come together, right? Because again, those oil droplets, if we leave them there, eventually they will come together. So how did they get together? This one is a tricky one. Yes? No? You're going to hate the answer. Randomly, right? The Brownian motion. As long as the temperature is above 0 Kelvin, there will always be some amount of energy kicking around in the system, and that energy, right, can bump into these nonpolar molecules, just randomly moving them all around. So it happens that randomly, when they happen to come together, now that state is lower energy. So there's nothing pulling them together. It's just at some point they happen to come together, and then now they're stuck because that's the lowest energy state of the system. And that's the hydrophobic effect. The hydrophobic effect is important for DNA because all of the bases are mildly hydrophobic. And the bases you saw before are pointed inwards. They're pointed inwards away from the water, right? This is what helps to give the DNA its structure. And this is what also helps to keep the two strands together, keeping both of these mildly inherently hydrophobic spaces inside, away from all the water, is more favorable than having them point out. So the formation of these double helices are the most stable state of the system in terms of hydrophobicity anyway. All right? And the same is true when we talk about proteins on Friday. The folding of a protein, the generation of its tertiary structure, which you're all going to get to understand when you read chapter 2, is driven by the hydrophobic effect. Some of the amino acids that make up a protein are very hydrophobic. They're non-polar. They want to be on the inside of the protein, while all of the polar amino acids want to be on the outside of the protein. This is what helps to drive the formation of the structure of proteins. All right. So for any of this to happen, again, we have to ask ourselves the question, is there enough energy for this process to occur, right? How can we determine if there's enough energy provided by the interactions to make a process proceed, okay? The change in free energy must be negative then for a process to occur. What is the free energy? Well, let's look first at entropy, right? So what is entropy? One word answer. What is entropy? Somebody shout it out.
Chaos. Disorder.
Chaos, disorder, randomness, right? And what always is happening in terms of randomness or entropy? Does entropy stay the same?
No.
Does entropy decrease? Does entropy increase? And how are any of you sitting here? You're a very complex system made up of many individual atoms and parts put together in a very specific way, right? Any other way, and you wouldn't be here. Wouldn't be able to walk around, wouldn't be able to think, wouldn't be able to see. So you've been put together. You are a walking contradiction, right? How is it that you are so complex, your body is so complex, if entropy is always increasing? Exactly. We are little entropy machines, right? I didn't say anything about where entropy must be increasing, just that entropy must be increasing. By you existing, right, is only possible because somehow you are increasing the entropy in the universe. So that process, you being alive right now, continues spontaneously. All right? So let's look at entropy here. The delta S, the change in entropy. Right, so if entropy is increasing, delta S is positive. If entropy is decreasing, delta S is negative. Right? This is inversely proportional to temperature, negatively correlated to the heat of the system. Right? So the heat, or the change in heat of the system. Again, if delta H is negative, that means heat is released from the system. If delta H is positive, heat is taken into the system. Right? Now, if we look at the total entropy in the universe, okay, well, we have entropy of our system, us, and the entropy of the surroundings, the universe. Right? So us and the rest of the universe, or a process and the rest of the universe. Depends on what context you're looking at. So delta S total then, we say that delta S of the surroundings is equal to what we said in the first equation, right? And delta S total equals delta S of the system, and I missed the delta there, minus delta H of the system divided by T, right? So all we're doing is substituting. Now we multiply both sides by negative T, we get negative T delta S total of the universe equals negative T delta S of the system plus delta H of the system, right? The heat of the system, right? So this is just algebra, nothing fancy going on here. Some guy named Gibbs long ago, chemist, decided he was done with this bullshit and said that he's just going to call negative T delta S total, that's Gibbs free energy, right? So the change in Gibbs free energy is equal to the delta H, the change in enthalpy of the system, minus T delta S of the system. Okay? So what does this mean? Well, for any process to proceed, delta G must be negative. Why? What could you tell me about either enthalpy or entropy if delta G is less And this is where Gibbs free energy really is kind of cool, right? So what if the entropy is increasing, say in making a whole body, right? So U existing, right? The delta S in that case would be negative or positive. Is entropy increasing or decreasing? Going from just a bag of chemicals to a fully made human being. Has the entropy increased or decreased?
Increase.
Decreased, because now we've ordered it in a very specific way. So entropy is decreasing because delta S is negative, right? The change in entropy will be negative. However, if we look at the Gibbs free energy equation here, delta G equals delta H system minus T, which is always positive because that's in Kelvin, so it has to be positive, right? T times negative whatever, right? So minus a negative number becomes positive, right? So let's say that delta H is 0, right? Let's just say that it's 0 for now. What will delta G then be, just in terms of sign? Be positive. So will we be able to make a thing, a person? No, delta G is positive, right? How then are we here? Well, delta G clearly must be less than 0, right? Because we happen spontaneously. So how can we make delta G be 0? Make delta H negative enough, right? So the delta H of the system, us, is negative. And what does that mean in terms of heat? Heat is released, right? And what are we always doing? Releasing heat, right? That's how infrared cameras work, right? Night vision works. We're always releasing heat. And why are we releasing heat? Because even though we are decreasing the entropy locally, right? The entropy of the universe is being increased because the delta H of our system, the body, is so negative. We release about 2,000 kilocalories per day, right? That's quite a lot. All right, so let's move on to acid-base chemistry, right? Which I'm sure everyone loves. So I want to spend just a little bit of time on this. I want to try to get to some examples if I can, but if not, we can do that in office hours or on Friday. Okay, so pH, very simply, right? If we have a strong acid or a weak acid, strong acid is easier to conceptualize and to think about. Say we have HCl. HCl in solution effectively completely deionizes into H plus and Cl minus, so whatever amount of hydrochloric acid or strong acid we started with will have that much H plus at the end because it completely dissociates into H plus and Cl minus. So let's say we started with 1 molar HCl, right? Well now, at the end, we'll have 1 molar, right? So if we have our initial, our change, and our equilibrium, right? So this goes down by that same amount, minus 1 molar, which means we get 1 molar H plus, 1 molar Cl minus. So at equilibrium, we have effectively 0 HCl left, 1 molar H plus, and 1 molar Cl minus. So to find out the pH of that solution, pH is simply P is a mathematical function which always just means negative log. So negative log of H plus, in this case, is 0. Right? Log of 1 is 0, negative 0 is 0. So pH of a 1 molar solution of hydrochloric acid is 0. But what if we have an acid that doesn't completely dissociate, right? So an acid that doesn't completely dissociate requires a little bit more care. So this is, for example, acetic acid. So acetic acid is CH3, COOH. This proton here is the proton that leaves, but it's actually very bad at leaving, right? So it doesn't completely dissociate the way that the proton on hydrochloric acid did, okay? And to what extent this proton leaves is just characteristic of that proton on this acid. Some acids, some weak acids have multiple protons that are ionized, right? We'll go over an example of that probably on Friday, right? But here, right, this dissociates into H plus and CH3, CO minus. This is called acetate. Here we have acetic acid, and here we have our proton. So let's say again, we start with 1 molar of acetic acid. Well, we can't just take negative log of 1 and say call it a day, right? Because this is not going to dissociate completely. So how much does it dissociate? This is determined by the acid dissociation constant, right? In this case, is the equilibrium constant for that dissociation. H plus times A minus the conjugate base, which in this example is acetate, divided by HA, which in this example is acetic acid. Now, for acetic acid, this Ka is 1.778 times 10 to the minus 5, right? So it's actually very bad at dissociating. So what is the pH of the solution then going to be? Well, now we put up our table, right? This is going to dissociate by some amount. We don't know what it is yet. But however much dissociates, well, we're going to get that concentration of H plus, so it's going to go up by that amount. This is going to go up by that amount. So at equilibrium, we'll have 1 molar minus whatever. We'll have whatever amount of H plus and whatever amount of A minus, in our case, acetate. So we just plug all this in, and we can say that 1.778 times 10 to the minus 5, the acid dissociation constant for this proton equals H plus, which we now know is X, times A minus, which is also X in this case, X squared then, divided by 1 molar, again, remember to do everything in molar, minus X. Now we have a quadratic, which is a nightmare, right? So you could, be fancy and a smart ass and try to actually do the quadratic, but you can do it the lazy way as well and say, well, this is so bad at dissociating that 1 molar minus X is going to be so close to 1 molar that we can just call it 1 molar, right? So just ignore that and be lazy. So now we have not a quadratic, so we can just say that X equals the square root of 1.778 times 10 to the minus 5, which I can't do in my head, but that's what X is. So now we know the H plus concentration. We take the negative log of that, and there we go, right? So let's see, square root. Now 2.4, right? 2.4 is the pH. Right? And because pH is a logarithmic scale, this is about 500 times less acidic as the 1 molar of hydrochloric acid. Right? So there we go. Right? This is how we deal with, with weak acids. Now, if we take that acid dissociation equation and rearrange it, we get something interesting. All right? Really annoying. Son of a bitch. Fine. Okay. So we have our weak acid, HA, right? Say acetic acid, whatever, doesn't matter. Associated to H plus. A minus, and we can say that the Ka of this, the equilibrium constant dissociation, is just H plus times A minus over HA, right? Easy enough. Now, let's rearrange this and say that Ka equals instead H plus times A minus over HA, right? So all we did was move this out down here. Let's take the negative log of both sides, right? So the negative log of Ka, let's just make our lives easy. Let's just take the log. The log of Ka equals the log of H plus times A minus over HA. And we know from our log rules, which everybody remembers from math, when we have log of A times B, that equals log of A plus log of B. So we can say that instead this is log H plus log A minus over HA. Right? Now, let's multiply both sides by -1. We get negative log KA, negative log H plus minus log A minus over HA. Well, now what do we have here? We have negative log KA, so let's just call that PKA, equals negative log of H plus, let's call that PH, and minus log A minus over HA. Let's solve for pH, and we end up with the Henderson-Hasselbalch equation. pH equals pKa plus log A minus over HA. And why did we go about doing all of this craziness here, right? That's because pKa is actually a very useful thing to know, right? So again, if we go back to the acid association constant of acetic acid, CH3COH, associates into H plus CH3CO minus acetate, the pKa of this proton is 4.75. How did I know that? Well, I know that the Ka is 1.778 times 10 to the minus 5. Take the negative log of this, it's 4.75. So the pKa is 4.75. And why is that so useful to know? Well, let's rearrange this equation and solve instead for A minus over HA. So A minus over HA equals 10 up to the pH minus pKa. Right? Everyone good with that? Everyone agree? I haven't done anything tricky. Well, now let's see what happens to the pH of the solution equals the pKa of that proton. Right? So again, the pKa of the proton on acetic acid is 4.75. So let's say that the pH is 4.75. So 4.75 minus 4.75 is 0. 10 to the 0 is? Right. So A minus over HA is 1. What does that tell you about A minus and HA? Huh? They're equal. They're the same. Right? So when the pH equals the pKa of that proton, A minus equals HA, right? That's a rule. And why is this important to know? Why is this good information to know? Well, what would happen if we decrease the pH? Just think, logically. Don't worry about the equation right now. If we decrease the pH from 4.75, what's going to happen to HA or A minus? Are they going to stay the same? No. All right, so then one of them must be getting bigger. Which one is going to get bigger? Raise your hand if you think A minus. Raise your hand if you think HA. All right, so why HA? You right there.
Because it's in an acidic solution.
Huh?
It's getting more acidic.
It's getting more acidic?
So more of the acid is produced.
All right, but try to be simple. Sure. Sure, but we didn't say anything about A minus. Let's think about it just logically. If we're decreasing the pH, what are we doing to the number of protons that we have per unit volume? It's increasing, right? So we have more protons. That means that some A minus is going to be converted to HA, right? And does that hold up? Well, let's see. We say pH is 4 instead of 4.75. So 4 minus 4.75. And what does that give us? Somebody got a calculator. What's 10 up to the negative 0.75? What is it?
About
0.178. Right? So, if this is less than 1, that means that HA must be bigger, and there we have it. And the same is true if we go the other way. If we increase the pH, then we lose that proton because A minus gets bigger. So pKa tells us something interesting about that proton. Below the pKa, that proton is typically there. Above that pKa, that proton is typically gone, right? So if we want to look at what the ionization state of a particular compound is, well, now we just look at the pKa and we say, all right, if the pH is less, then that proton is there. If the pKa is higher, or the pH rather is higher than the pKa, then that proton is gone, right? And how do we know that? Well, using the Henderson-Hasselbalch equation, right? That's what this tells us. And that's why pKa is so useful. As we'll see when we talk about amino acids in chapter 2, many of the amino acids have ionizable protons, right? In particular, histidine is of great importance because it's got a proton with a pKa of about 6, right? It's the only one that's got a pKa that's about 6. Why do you think that is interesting or important? Well, what's going to happen to that proton at pH above 6? Be gone, and at pH below 6 is going to be there, right? And that proton is actually on a nitrogen. And why is that cool? Because now we have what? We have a hydrogen bond donor that we can turn on and off. Because that pKa is at 6, which is very near 7.4, which is what our bonds are typically at, all right? Well, now, especially in that electronic environment that histidine finds itself, now we have something that can serve as a hydrogen bond donor sometimes or not sometimes, right? We can turn it on and off. So we'll see that. So understanding pKa is important. Additionally, pKa gives us a way to use buffers, right? So buffer solutions, like the phosphate buffer that we find in our blood, all right, functions off of these weak acids. A buffer is something that simply just buffers against changes in pH, and they're made up of dilute solutions of weak acids. And why is this the case? Well, let's imagine that we have, again, a solution of acetic acid at pH 4.75. So we have equal amounts A minus and HA, right? So now if we add acid, I say that we have now 0.5 molar A minus and 0.5 molar HA, and we add acid to a final concentration of 0.1 molar, well, really, all that's going to happen is that that acid is going to convert 0.1 molar of A minus into HA, right? So let's say that we start at pKa, again, 4.75. We have a 1 molar solution, so we have 0.5 molar A minus, which is acetate. And we have 0.5 molar acetic acid. Right? And now we add acid to a final concentration of 0.1 molar. Well, now, 0.1 molar of this is going to be converted into HA. So we'll have 0.4 molar acetate and 0.6 molar acetic acid. Right? So we have changed the ratio here, but because that A minus over HA is in the log, right? Even though we changed that ratio, the overall pH doesn't change that much, and that's what you see on the screen right there, right? So we have acetic acid at pH 4.75. Over here, about 1 pH unit above and below the pKa of that weak acid is what we call the buffering zone. That's when the ratio of A minus to HA is sufficient so that it can absorb enough H plus or donate enough H plus if we add base in order so that the pH doesn't change appreciably. Now, once we get out of that pH range, so say that we have acetic acid at pH 7, well, at pH 7, we're mostly acetate, aren't we? Right? We're mostly acetate. We have very little HA. So we do have some protection against adding acid, but we have no protection against adding base, right? So buffers are only really effective at pH levels near their pKa's. And this is what we see over here. This is the phosphate buffering system. This is what we find in our blood. Notice here, phosphate, like I mentioned before, phosphate is one of those compounds that has multiple ionizable protons, right? In fact, these protons over here. So the first one that leaves, right, H3PO4, we lose the first proton. That first proton's got a pK of 2.12, right? So as soon as we pass pH 2.12, now we're mostly in this form here, H2PO4. Then we lose the second proton. The second proton has a pK of 7.21. Now we're over here, right? We lose the third one, it's got a pKa of 12.67, and now we're only at phosphate over here. So, why does this matter? Well, if we only adopt this form here, so we have a pK of 7.21, we get rid of the first proton, and now we're only dealing with the second proton. Well, now this becomes an effective buffer at pH 7.21, or more specifically 7.4, which is biological neutral. That's what pH your blood should be at, right? This is what helps keep that pH in check, right? Because this is a weak acid, it's got a pKa of right about where we want, 7.21, 7.4, thereabouts, right? Having phosphate in our blood helps to protect the pH, to make sure that it stays at pH 7.4. Why is it important that our pH is buffered or regulated? Well, low pH or high pH can denature protein, it can denature DNA, right? We'll read that in chapter 1. Okay, so maintaining the blood pH and the cellular pH at that level is critical to make sure that our enzymes and proteins can still function. All right? So unfortunately, we didn't get a chance to do the practice problem today because there's too much time to lecture. I'm going to get better at that. We will do some practice problems at the beginning of class tomorrow before we get into practice.